So, just to summarize the portion covered in this set of lectures. So, we talked about creep curve, we talked about the equation of creep, the strain rate equation, we talked about factors, and also we talked about types of creep curves. So, now a small tutorial or some numericals related to the portion that has been covered so far. So, the first question relates to logarithmic creep. So, the question is, please draw the strain rate versus strain curve for a material that is experiencing logarithmic creep. So, a general creep curve you have primary, secondary and tertiary, and if you plot the strain rate versus strain for a regular creep curve, this is how it will look like. This is the primary creep stage, secondary creep stage and tertiary creep stage. Now, in this question I am asking you to plot the strain rate versus strain curve for a material that is experiencing logarithmic creep. So, if you remember, we said logarithmic creep is also known as exhaustion creep. So, in exhaustion creep the material continues to come down in strain rate of deformation. So, it does not achieve a steady state of creep. So, the strain rate of deformation continues to decrease, it is also known as exhaustion creep. So, the strain versus time would look like that. So, for logarithmic creep the strain rate versus strain curve would look something like that. So, it will continue to go down in strain rate as plastic deformation happens. So, that is how a material that is experiencing logarithmic creep or exhaustion creep, the strain rate versus strain would look like. Alternatively, if you plot strain rate versus time, even in that case you will see something like that. So, that was question 1. So, now let us move to question 2. So, the question 2 is about between the two curves shown below. So, in this case I am showing you two curves, one in red and one in blue. So, the question is which one corresponds to constant load tests and which one corresponds to constant stress tests, and also please explain your answer. Now, what is the main difference between a constant load and constant stress test? Obviously, in a constant load test the load that you apply at the beginning of the test, say P, is going to stay constant till the end of the test, creep test, whereas in a constant stress test the stress that you applied sigma is going to stay constant, which means as the material starts deforming and as the cross section comes down, you will also have to change the applied load accordingly, so that the stress remains constant throughout the test. So, the answer to the question is, this is a constant load test and this is a constant stress test. So, the creep curve here corresponds to constant load, the creep curve here corresponds to a constant stress. So, the time to failure in a constant load test will be lower compared to the time to failure in a constant stress test, and also the material reaches the tertiary creep regime faster in a constant load test compared to a constant stress test. So, the explanation is as follows. So, you have say the initial cross sectional area was A naught in both cases. So, constant load the applied load was P in both cases, and since P is going to stay constant, A naught as the material starts extending, the cross sectional area is going to come down. So, initial stress sigma I for a constant load test is P over A naught, and the let us call it sigma naught. So, initial stress is sigma naught and instantaneous stress. So, stress at any point sigma I is P over A I, and since A I is going to be lower than A naught on account of the fact that the material is extending. So, sigma I is going to be greater than sigma naught. So, what this also means is, since the stress is constantly increasing in a constant load test, the strain rate of deformation, since strain rate of deformation is a function of sigma and say it relates to stress by that relation. So, epsilon naught is going to be some form of dependence on stress is sigma to the power n. So, as sigma increases, strain rate of deformation also increases. So, as the strain rate of deformation increases, the material is going to go towards failure faster. So, for the same strain, so if the failure strain is epsilon and if the strain rate of deformation is increasing, so epsilon f is equal to some strain rate into time to failure T f. As epsilon dot increases, the time to failure is going to come down. So, that is what is happening in a constant load test. Now, let us look at the constant stress state condition. So, test condition. So, you have A naught and applied load is P, the initial stress acting on the applied stress is P over A naught. As the material elongates, so the cross sectional area is going to become A I and instantaneous stress sigma I is equal to, so the cross sectional area is A I. So, the instantaneous stress should have been P over A I, but because you are trying to keep it constant equal to sigma naught. So, you have to reduce the applied load. So, P I is going to be lower than the applied load P naught. So, you constantly regularly reduce the applied load, so that you can keep the stress constant, and because you are reducing the applied load and keeping the stress constant. So, again epsilon dot is equal to some function of stress. So, it say sigma to the power n, since sigma is constant. So, epsilon dot is going to stay constant till a point, and so what happens is the time to failure, and since epsilon dot here in a constant stress test is going to be lower than in a constant load test. So, therefore, the time to failure in a constant stress test is going to be greater than the time to failure in a constant load test. So, this is in brief the difference between the two type of creep curves, constant load as well as constant stress type of creep curve. So, you are basically entering into tertiary creep lot faster in constant load test, and of course, this description we are talking about tensile creep test. Now, let us look at question 3. So, this also relates to the constant stress and constant load kind of testing. So, the question is as follows. So, it was decided to conduct tensile creep tests under a constant stress mode on a dead weight creep machine. So, the specimen were cylindrical in nature. So, the cross section is that cylindrical in nature with a diameter of 4 mm and a gauge length of So, say the gauge length was 100 mm. So, if the plan was to conduct creep tests under a constant applied stress of 100 MPa, what should be the initial applied load and what should be the load applied after the material has experienced 5% creep strain. The question is, initially for that cross section of material, what should be the load applied, so that your stress sigma is equal to 100 MPa, and how much should the load be after the material has experienced 5% creep strain, so that the material continues to experience a constant stress of 100 MPa. So, let us look at the solution. So, the important thing here is to remember plastic deformation, the volume of the material is constant and the volume of the material is a product of the cross sectional area and the length that is under testing. So, here the cross sectional area A is equal to pi d square by 4. So, that gives you d is equal to 4 mm. So, that gives you 3.14 into 4 in. So, and volume will be A into L. So, that will be pi d square by 4 into gauge length L. So, essentially you get 1256 millimeter cube. Now, for a constant applied stress of 100 MPa, the initial applied load. So, the initial applied load for the first bit. So, the applied load should be P is equal to sigma times A. So, that is 100 MPa into 12.56 millimeter square. So, that makes it 1256 newtons. So, for a constant applied stress of 100 MPa, the initial applied load should be 1256 newtons. Now, second bit, after 5% extension, what should be the applied load? So, we are talking about a strain of 5%. So, plastic strain so this implies epsilon is equal to 0.05 and plastic strain is defined as ln or L over L naught. So, L is the instantaneous length, L naught is equal to initial length. So, therefore, L is going to be L naught into e to the power 0.05. So, the instantaneous length of the sample is going to be 100 into e to the power 0.05, that makes it 105.1 millimeter. So, the instantaneous length or the length of the sample after 5% extension is going to be 105.1 mm. So, when the material has extended in length, at that point what will be the cross sectional area of the sample. So, by considering constant volume conditions, so the length of the cross sectional area will be the volume divided by the length after 5% extension. So, that is going to be 1256 divided by 105.1. So, the cross sectional area A I corresponding to instantaneous length of 105.1, the cross sectional area will be 11.95 millimeter square. Now, since it is a constant stress test, so we are going to keep the stress constant at 100 MPa. So, to keep the stress constant at 100 MPa, the load that needs to be applied after 5% extension is the stress into the cross sectional area corresponding to 5% extension. The cross sectional area corresponding to 5% extension is given here 11.95. So, the load will be, the applied load should be 100 into 11.95. So, that makes it 1195 Newton. So, the applied load at 5% extension should be 1195 Newton. So, that the material continues to be in a constant stress condition. So, that is the solution to this problem. Okay, let us look at question 4 or problem 4. So, this corresponds to this question relates to logarithmic creep behavior. So, here we are talking about a material that is displaying a strain rate of deformation of 4.5 into 10 to the power minus 7 seconds after a time of 100 hours under an applied stress of 45 MPa. And the question is, what will be the strain rate of deformation after 200 hours? That is part 1 of the question. And part 2 of the question is, if you are designing a component that should experience a maximum allowed strain of only 0.25 after 10,000 hours, do you think the above material will meet this criterion or not? So, essentially the question is, how much will be the strain, how much will be the creep strain after 10,000 hours? Is it going to be greater than 0.25 or is it going to be less than 0.25? If it is greater than 0.25, then obviously your product is not going to survive 10,000 hours of operation. If it is less than 0.25, then your product or your component is going to survive 10,000 hours of operation. So, basically these are the two parts. First part is find out the strain rate of deformation after 200 hours. The second part is find out the plastic strain after 10,000 hours of operation and check whether it is meeting the required performance of only 0.25 plastic strain. So, we are going to solve this in the next page. So, and the logarithmic creep curve is defined by epsilon is equal to epsilon naught plus ln alpha ln 1 plus gamma t. We have already given epsilon naught value and alpha value. Epsilon naught is equal to 0.01 and alpha is equal to 0.5. So, epsilon is equal to epsilon naught plus alpha ln 1 plus gamma t. So, the strain rate of deformation epsilon naught dot is going to be d epsilon over dt, that is equal to d of epsilon naught plus alpha ln 1 plus gamma t over dt, that is equal to d epsilon naught over dt plus alpha d of ln of 1 plus gamma t over dt. This is a constant equal to 0. So, that it basically comes out as alpha into gamma over 1 over 1 plus gamma t. So, the strain rate of deformation is given by that equation. Now, the strain rate of deformation after 100 hours is epsilon dot is equal to 4.5 into 10 to the power minus 7. So, this implies 4.5 into 10 to the power minus 7 is equal to 0.5, that is the value of alpha, into gamma. So, we do not know gamma. So, 0.5 into gamma divided by 1 plus gamma into 100 hours. So, 100 is 100 into 3600 seconds. So, 1 hour is 3600 seconds. So, 100 hours is 100 into 3600 seconds. So, this will give us gamma. So, 4.5 into 10 to the power minus 7 plus gamma into 100 into 3600 into 4.5 into 10 to the power minus 7 is equal to 0.5 into gamma. This implies 4.5 into 10 to the minus 7 plus gamma into 36 into 10 to the power 4 into 4.5 into 10 to the minus 7 is equal to 0.5 gamma. This implies 4.5 into 10 to the power minus 7 is equal to 0.5 gamma minus 0.162 gamma. So, this implies gamma is equal to 4.5 into 10 to the power minus 7 divided by 0.338. So, that gives gamma as 13.3 into 10 to the power minus 7. So, that is the value of gamma. So, now, the first part is find out the strain rate of deformation after 200 hours. So, if you look at the question, so it says what will be the deformation rate after a time of 200 hours if the material is displaying a logarithmic creep behavior. So, now what we have with us is we know the value of alpha, we know the value of gamma, we know the value of epsilon naught. So, therefore, strain rate which is equal to alpha gamma by 1 over 1 plus gamma t. So, alpha gamma by 1 plus gamma t is epsilon dot. So, epsilon dot is equal to, so we know the value of alpha which is 0.5. We now know the value of gamma which is 13.3 into 10 to the power minus 7. So, divided by 1 plus 13.3 into 10 to the power minus 7 and time is 200 hours. So, 200 into 3600. So, therefore, the strain rate of deformation after 200 hours is equal to 6.6 into 10 to the minus 7 divided by 1 plus 13.3 into 72 into 10 to the minus 3, 13.3 into 72. So, that is equal to 6.6 into 10 to the minus 7 by 1 plus 0.957, 6.6 divided by 1.957. So, that is equal to 3.37 into 10 to the minus 7. So, the strain rate of deformation after 200 hours is 3.37 into 10 to the power minus 7. So, if you observe the strain rate of deformation after 100 hours was 4.5 into 10 to the minus 7 and the strain rate of deformation after 200 hours is 3.37 into 10 to the power minus 7 seconds. So, the strain rate is decreasing and that is what you expect in a material that is exhibiting logarithmic creep or experiencing exhaustion creep. So, the strain rate of deformation is 3.37 into 10 to the minus 7. Now, let us look at the second bit of the question which was about finding out if the material is going to experience a maximum strain of only 0.25 or is it going to experience higher after 10,000 hours of operation. So, basically the question is finding out epsilon after 10,000 hours of operation. So, all that we have to do is we have to input epsilon naught value, alpha value and then find out ln of 1 plus gamma t. So, epsilon we know epsilon naught is 0.01 and alpha we know is 0.5 and ln of 1 plus we already know gamma is 13.3 into 10 to the power minus 7 and time is 10,000 hours. So, it is 10,000 into 3600. Therefore, epsilon is going to be 0.01 plus 0.5 times ln of 1 plus 13.3 into 10 to the minus 7 into 36 into 10 to the power 6. So, that makes it 0.01 plus 1. Plus 1.94. So, the overall it becomes 0.01 plus 1.94, that is equal to 1.95. So, that is a lot of plastic strain that the material is going to experience, and it is clear that this value 1.94 is going to be greater than the 0.25 value that the engineer was planning on designing the component for. So, the maximum strain that you wanted or the engineer wanted was only 0.25, but what you have found out is after 10,000 hours of operation, the material is going to experience 1.595 times 1.95 plastic strain. So, clearly the above material will not meet this criterion. So, the material is creeping a lot higher than what you wanted it to. So, you have to discard that material. So, this was about question 4 and how to use equations such as this to determine the creep behavior of the creep strain of a material. So, now let us look at another question which is also similar in the sense you are going to talk about you are trying to find out the amount of plastic deformation the material is going to experience, and here you are going to use a creep curve. So, here is how the creep curve looks like, and I have given you some numbers. So, it is experiencing a plastic strain. So, this is going to be percentage. So, it is experiencing a plastic strain of 2% after 20 hours, and it is experiencing a plastic strain of 2.5% after 60 hours of operation, and experiences around 3% plastic strain after 85 hours of operation. So, the first two, if you see, this is in the steady state creep range, and 3% the material is already in the tertiary creep range, and the question is, in the given problem, find out the actual time taken to 3% creep strain. So, the actual time taken to 3% creep strain is you can directly find it out from the figure. So, it is around 85 hours approximately. Now, how much is the time taken to 3% creep strain based on steady state creep rates? Now, in lot of times engineers tend to design their components based on the steady state creep rates. The reason is you can achieve your steady state creep rates. Typically creep experiments can last very long, and by the time you go to a tertiary creep regime and failure, it may take you at least a few hundreds of hours. And when you are trying to if your program is accelerated, in the sense you are trying to develop a product quickly and you want to know the behavior of the material in quick time, you cannot wait or you cannot afford for the material to go till failure, because in that process you are going to spend months of time just to get an understanding, basic understanding of the creep behavior of the material. So, typically what engineers tend to do is they allow the material to enter into the steady state creep range. So, once the material goes into steady state, then they are going to use, and you know that in the steady state region the strain rate of deformation is going to stay constant for a fairly long time. So, then you can use the steady state creep rate and get an approximate idea of how much time it will take for the material to reach a certain level of plastic deformation. So, that is what we are going to do in this question. So, we are talking about the time taken to 3% creep strain based on steady state creep rates, and finally, if the factor of safety that the engineer has with him is 1.5, what will be the useful service life of this material. So, these are the 3 bits to this question. Now, first bit I already answered. So, the first bit is 3% strain. So, 3% strain, it takes you around 85 hours, 85 to 87 hours. So, the material reaches a plastic strain level of 3% in around 85 to 87 hours. Now, the second bit is how much is the time taken to 3% creep strain based on steady state creep rates. So, let us now try to find out the steady state creep rates. So, at 20 hours the plastic strain 20 hours is 2, at 60 hours the plastic strain is 2.5. So, the strain rate of deformation in steady state is equal to delta epsilon by delta t. So, that becomes 2.5 minus 2 divided by 100, and then delta t is 60 hours minus 20 hours. So, that is equal to 0.5 divided by 100 into 40, and this is per hour basis. Now, your goal is to find out how long will it take to reach 3% creep strain. So, your strain is 3%. So, that is 3 by 100, and you want to know how long will it take to reach 3%. So, the time taken to reach 3% based on steady state creep rates will be equal to the strain divided by the strain rate. So, the strain is 3 over 100, and then you divide it by 0.5 by 100 into 40. So, you get 240 hours. So, the time taken to reach 3% plastic strain is equal to 240 hours. So, that was part 2 of the question, and then let us look at part 3, which is the factor of safety. So, if the factor of safety is 1.5, what is the useful service life of this material? So, we are talking about 3% creep strain. So, the factor of safety we are going to use with respect to 3% creep strain. So, if you are allowed maximum plastic deformation of 3%, and what we see is the actual time taken is only 85 hours, and since the engineer has to use a factor of safety of 1.5. So, therefore, the useful service life of the material is going to be 85 over 1.5. So, that will turn out to be 56.6 hours. So, it is 56.6 hours, assuming that the maximum allowed strain is only 3 hours 3%. So, the maximum allowed strain